Well, thank you. It's always a great pleasure to give a public lecture like this because the audience is not the audience usually a professor will be giving talks to. This indeed present a great challenge for professor. I actually got quite a bit of training in order to give a SLAC public lecture. We have a great team right here in SLAC National Lab. But Michael and the team invited me to talk about batteries. Indeed, if you look back about 6 years ago, I gave a public lecture like this topic. I was thinking, what's really new I can tell you, or deeper things I can tell you. Indeed, in the past 6 years, many great things happened. Well, you see electrical car really took off, right, in a big way globally. So that's quite a difference right there. And since last year, I took on the director position for at the Preco Institute for Energy. This allowed me to look at broader and the energy transformation, going from fossil fuel to the clean energy. And with an even bigger picture, well, the battery research, what can it really do to impact the society? So let me share with you this first slide. And the big picture, the global commitment to the net zero. Net zero means net zero carbon emission by certain time frame. 2050 is Paris Agreement. The US was back to Paris Agreement. These are the major countries, the emitters, contribute to the carbon. They all committed by a certain time frame. And 60% of Fortune 500 companies also committed to climate goals. And if you look at this global commitment, energy industry contribute to somewhere more than $30 trillion per year. And then looking at where CO2, carbon really come from, these two sectors stand out the most: transportation, electricity, your electrical grid. If you could decarbonize these two, you decarbonize half, a little bit more than half of the global economy already. So it's very, very important. Of course, other sectors are important as well. Industry, like steel making, cement making, plastics, these are all important. And agriculture and the building as well. So, and to decarbonize these two, batteries actually play a very important role. And on the top row is the application that's for portable electrical transportation right here. And also airplanes. We don't know how to do that yet. That's why people draw two batteries right there. It's actually a very challenging problem potential batteries can impact. And stationary energy storage to integrate solar and wind electricity into the electrical grid, this intermittent source of energy, electricity, this is required to store the energy. So it becomes very clear for the modern society how important the batteries are. But when I started 17 years ago at Stanford, I was the only person to work on batteries other than about 1970s. We have a senior faculty in the department working on that. He retired. And then when I joined the faculty in 2005 to launch a program on battery, I didn't know it was so important. But nowadays it's very, very clear. So let's look at, what are you looking for the batteries? There's certain parameters you need to define, then you know, well, these batteries are good, that one are not so good. What are you looking for? You are looking for first is how much energy do you store for a given weight or given volume of the batteries. Measure using watt hour. You're familiar with kilowatt hour, right? This is a watt hour and per kilogram or per liter. So one is gravimetric, the other is volumetric. For your cell phone, you probably don't care about the weight as much. It's actually the volume. If you are limited for the car, you are limited by both. You care about both weight and volume. Cost is also important. Imagine using how much per dollar per kilowatt hour. If you have a really battery size, like store certain energy, how much do you pay? Lifetime, cycle life. Cell phone, usually you do one charge per day. Electrical car, maybe you do a charge per week or a couple of charges per week. And then calendar life is how many years this will last. And they are correlated, but they're not exactly the same. Some batteries can have long cycle life, but short calendar life. If you just let it sit right there and wait for a couple of years, the battery could die, even if you don't use it. So charging rate is important, right? We talk about now typically an hour or two. Tesla, the fast charge, 30 minutes can get you probably about 60 to 80% if you do their fast charging in their station. And then safety, you care about safety. Catching fires, explosion, these are the problems you care about. So these are the basic parameters you ask first. And then now let's come back to what exactly, how are we going to do innovation? You say, well, you hear about all kinds of batteries, but common one is lithium ion. You heard about lead acid batteries. In the past, you know, there's a nickel metal hydride, there's a nickel cadmium, there's alkaline battery, there's all kinds of chemistry. What's really going on? How do you choose? Why people develop this different set of chemistry? Let's look at how you store electrons first, store this electricity. Well, let's come back to very, very simple chemistry. What you want to store is electron, that's tiny e right there. But they have negative charge. If you put two negative charge together, they repel each other. And how do you put a lot of them, stack them together? Not possible. Then you say, let me balance the charge, make it charge neutral. You need to put something that's positive. Positive charge, that's ions. Right? This could be lithium ions. It could be hydrogen ions, that's proton. So to balance this charge, maintain charge neutral. So you can store a lot of this together. However, what you are paying, the price is so big. Electron is very lightweight, but iron is thousands of times, 10,000 times heavier. So you are paying a lot to store that electrons. Not only you are paying a lot by these ions, you also need to have electrons and ions to store, I call it as a host. Let them all come in to meet, get stored. This host can be also very, very heavy, very big. You pay even more in order to store the electrons. I mean, the whole game of innovation becomes, hey, let's pay as little as possible. Let's pay as little as possible to store the electrons. So what are the choices? Let's come back to chemistry. Well, first of all, let's use atomic weight. I want to pick those very lightweight, very small ions, so I pay less. So the lightest one is proton, is hydrogen, with atomic weight that's 1. Once you use proton, oftentimes that technology is called fuel cell technology, hydrogen fuel cell, right? You use proton for doing that. And then if you use lithium ion, now atomic weight 7, it's much more heavier. But that's the next to a proton, the best you can do. That's lithium ion batteries. Then you say, well, I want to pick sodium, atomic weight 23. That's a lot heavier. That's your sodium ion batteries. If you say, I want to pick lead, that's really big, very heavy one. Hey, that's your lead acid batteries you use in your car, gasoline car, to start the engine. That's your lead acid batteries. The way you pay is just going higher and higher. These are all the research now batteries. Exist zinc ion, zinc metal, aluminum, magnesium. These are all ongoing. So there's a lot of choices. But lithium ion is favored, and proton fuel cell is favored. Let's look at this other reason, other consideration we need to
talk about. And then what's the maximum voltage per battery cell you can have? What decide that? That's actually in chemistry, there's a term called electronegativity or electropositivity. The ability of this element, they can keep electrons or giving electron. That ability determine at the end what's the voltage of your cell. So lithium is the one. They don't like electron. They like to give electron away. So the potential is very low. They don't want to keep electrons at all. Eventually, you make a battery cell. This is used as a negative electrode using lithium metal. And then you have a positive electrode right there. You can build a high voltage cell up to roughly within this range, 4.5. That's the highest one you can find. That's why this is favored in your consumer electronics and your cell phone, because you need to have high enough voltage to power your transistor, power your semiconductor chips. Having one cell, you say, why don't I use multiple cells connecting in series? You could do that, but you pay the penalty. You need to pack so many, it's not convenient, the cost will be very high. So proton, even though it's lightweight, we know in water, it's limited by the water, how stable that is. If you put 2 electrons into the water, right? You're going to split water, generate hydrogen. Usually, it's about 1.5, usually. So lithium is favored in this case. But when you look at the cost, lithium is highest one, right? Proton from water is nearly free if you're charged back and forth. It's really nearly free. So from the cost standpoint, lithium is not so good. But lithium so far probably occupy the battery called lithium-ion battery is about 10%. In the past, it's less than 3%. In the past 2-3 years, lithium price goes skyrocket. And it occupies bigger percentage of the cost right now. So with this consideration, and there's a reason why lithium-ion battery is dominating, it's offering you this very light element, even though it's not as light as hydrogen, but it's the next lightest one you can find. Lithium-ion can move very fast. So if you take this material, you say, well, let's look at the real battery cell, right? This is a typical cylinder cell. The size, I put it right here, it's called 18650. It's 18 millimeter in diameter here, 65 millimeter in height. This is the cell Tesla packed 7,000 of these batteries together, put into the Tesla car at the beginning. Now Tesla go to slightly bigger cell right now, but the idea is similar. If you cut it open, you're going to see this multi-layer of this metallic foil, a copper foil, aluminum foil, it coated with materials. There's a polymer layer, this blue color is a porous polymer as a separator. Separate copper electrode from aluminum electrode, prevent shorting and roll together. If you zoom in further, just look at this cross section on top of copper. There's a layer of materials right here. This is graphite. Graphite is the host materials to host electrons and lithium together to every 6 carbon. When you do the battery charging, electrons and lithium all go to this graphite particle and get stored right there. When you do discharge, electron will return to this side, and the lithium will return to this side and forming this lithium cobalt oxide. Actually, these 2 materials are the basis for the initial lithium-ion battery commercialization. These are also the important materials. 2019 Nobel Prize was given to lithium-ion batteries, and using the invention of this type of material really enabled that. Oh, and also, by the way, you happen to sit in this week, right, this lecture. This is the week of Nobel week. Right? Since Monday until today, you see one Nobel Prize announcement day by day. So in order to have this all work out, inside here, you see the separator, lithium shuttle back and forth, electron coming back and forth during charging, discharging. And the fundamental thinking is how you got to move the electrons. Electrons should be able to travel from one electrode to the other electrode and then go into this particle during charging. And lithium should be able to move from right-hand side to the left-hand side, inserted into this particle. and electron and lithium will meet right there, right? So these are the two basic process got to be happening. You say, well, isn't that really easy? No, it's not easy at all for some materials, because if you look at graphite, that's easy because graphite is very conducting. Lithium cobalt oxide is reasonable, also quite conducting. But for some of the exciting materials you want to produce for the battery technology, they are not necessarily that conducting. You need to understand why they are not conducting. How do you make them conducting? And then through this process, because lithium electron coming in and out, they have volume, they have size. They're going to cause structural change. They're going to cause this particle breathing, become bigger, smaller during charging, discharging. These all happen at the same time. Not only that, each of these particles, particularly on the anode, the negative electron side, graphite, with the electrons right there, very reactive. This electron will like to react with this electrolyte, liquid electrolyte, soak into these batteries and generate a self-decomposition compound. This particle surface coated by a layer of very, very thin coating. That is called solid electrolyte interface. We also call it SEI. This interface is the gate for lithium ion going in and coming out. This layer is very, very important. If this layer breaks, that electron can leak out, react with more electrolyte. If this layer doesn't conduct lithium that much, make it harder for lithium to go in, it's very hard for you to charge and discharge your battery. So this layer is very, very important. So looking at where we are right now, right, in those parameters, we are roughly about 250 watt-hour per kilogram. Can we double that? Get to higher and higher energy density. We are roughly about $130 per kilowatt hour in the cell level. Can we reduce that by multiple times? So then the electrical car will be much cheaper. So far, the battery pack occupies a really big fraction of the cost. And 1,000 cycles, 7 years. Can we go to 10,000 cycles, 30 years? 1 to 2 hours charging usually. Can we do within 10 minutes? Very fast charging. Then it's almost similar as, go to the gas station, adding gasoline, right? That's a few minutes type of feeling. And from not safe to completely safe. Well, these are the questions we want to answer. These are the technologies we would like to develop. Of course, it's very hard to have everything all together within one technology. I would say if you can make certain parameters reasonable, you can improve one parameters in a dramatic way. That's already a breakthrough for the battery technology. So in today's topic, with that introduction, let me share with you these questions. I want to provide some answers to you. Is how high energy can we go with the existing chemistry we know? How do we really understand what happened inside the battery? I want to present to you a new tool that can get you to the level you've never seen before and help you to extend the battery life, help you to understand the battery safety. That's cryo-electron microscopy. And we have a national facility right here at SLAC National Lab, very powerful tool. Battery safety, everybody care about. I'm going to touch upon that. And also grid-scale energy storage. How do you store solar and wind electricity? Really big battery farm. What's the technology available for you to do that? And eventually, let's come to the last topic, scaling and circular economy. Because the whole world is going through global clean energy transformation, we need to store a lot of clean electricity, and the battery pack will be big, battery farm will be big. Can we really get there with the resources we have? So let's look at the high energy density one. This is where we are right now. If we can double this huge meaning right there, the driving range of the battery car, roughly double. If we can go to 4 times of the current technology, go to 1,000 watt per kilo, and the next time I go to Boston, I probably will be taking an electrical plane, right? So this is the impact you can imagine we might have. So high energy density is very important. So how do you increase the energy you store? Energy E right here, right? This is a high school physics, equals to voltage multiplied by charge, that's Q. You want a high voltage batteries? You want to store as many charges as possible. So that is what you need, high voltage, store a lot of charge, and you want the lightweight, the host material to be lightweight. And the volume needs to be small. Then you can have high energy density. So this is used in the current technology. This is graphite used in anode and the lithium-ion batteries. This is this carbon atom forming covalent bonding right here. This is so-called graphene layer, and this layer stacked together forming graphite, right? And lithium coming in, stored between the graphene layer, hiding between the space, giving you this 370 milliamp hour per gram. So battery field has this very strange unit, not traditional, but it's very convenient to use. Milliamp is current, hour is time, current times time give you charge. So that's the unit we use a lot. But futures, sorry, this typo right here, future anodes, silicon can store a lot more, 4,200. Metallic lithium store also very high. So if you can make these two work, you can store 10 times of the current technology. So that's very attractive to work on new materials, silicon and metallic lithium. On the cathode side, lithium cobalt oxide, lithium manganese oxide, lithium iron phosphate, this amount of charge, let's say close to the neighborhood of 200 milliamp hour per gram, right? This has been the power, really, this has been the very important material, really power your devices. You know, lithium iron phosphate is used in electric car a lot. Lithium cobalt oxide is used in your cell phone. And the variation of lithium cobalt oxide now is used a lot in your electric car. So what if you can make something like sulfur? That could work. This offer this gigantic charge storage capacity, which is about also 10 times of existing technology. And also, by the way, sulfur is so low cost. It's so abundant. This transition metal right here, cobalt's cost will be too high. When you go to scale, and you need to think about abundant material, low-cost materials. So can we make these new materials to work? If we could, these pathway might be possible. Going from current technology of 250 watt per kilo with this nickel manganese cobalt oxide, right? Graphite anode MMC, this is MMC. If silicon coming in, paired with MMC, you can get to 400, maybe slightly higher. Metallic lithium coming in, 500 lithium metal sulfur. Can we enable 600 to 1,000 watt per kilo? Before my retirement, I really like to take electric plane from West Coast to the East Coast, right? That's a dream before I retire. Michael, I still have some time, but what are the problems? Why we couldn't use those new materials? It's really because they store so many lithium ion compared to traditional material. Traditional material hosts, they're stable. In the past 30 years, we have been using that, right? Graphite, lithium cobalt oxide, they don't store that much lithium. They're stable. The new materials coming in, lithium coming in, right, into this new material, or just break all this chemical bonding. I go, that's crazy, right? You break these host materials. And then these host atoms, silicon, just moving around, lithium moving around, completely crazy. And complete structure change, gigantic volume expansion. In the past, the old materials, all less than 10% volume expansion once you have lithium coming in. The new material go to 100%. And it could even go higher, 400%. There's so much more expansion you need to overcome. How do we do that? I mean, that's completely crazy to think about it. So 2005, I joined in as a faculty. It's good to be a young faculty. You are not afraid of anything. That's why you want to hire young people into your group, because they come in, they don't know enough yet. So they say, I can make anything happen. I really need to have high school students to get into the field very, very soon. They are not afraid of anything, right? That's the best. If you are not afraid of anything, the possibility is there to solve the problem. If you are getting to, too much later in your career, you say, I've seen this doesn't work, that doesn't work. So it really doesn't work if you think this way. So silicon, let's come back to silicon. Silicon can store so much lithium. And because one silicon atom can combine with 4.4 lithium ions, 6 carbon can only combine with 1 lithium. So silicon store a lot more. But because it stores so much more, the volume expansion of single silicon particle, you put lithium in, volume expansion to 4 times, blow it up, they're going to break. Once they break, this particle pieces, the dead body, they're not connected with each other. You cannot get electrons in anymore, right? You really cannot. Remember I told you, the first requirement is make sure electrons can go in. If they are loose contact, they are not going to be able to go in. The battery die. The second thing is, what is solid electrolyte interface, SEI? Let me emphasize this parameter again. You need to form a stable layer on the surface. If this volume expansion is happening, how could you form a stable layer, particularly if silicon is breaking? There's no way. So the surface of silicon will continue to react, is soaked into the liquid electrolyte, continuously react with liquid electrolyte, decompose electrolyte. The batteries also die fast because your electrolyte will dry up. You consume lithium. So back in 2018, January, we published the first paper. That was about 2.5 years after I joined in faculty. This was my first batch of graduate student. She's a faculty member at Arizona State right now. We use this silicon nanowire structure. Diameter is very small. And grow this wire, the bottom, they are in contact with this metallic foil current collector. Now you can ship electrons in and out. This is continuous pathway. And then you can relax the stream because volume expansion take place, it can break. But once you make it small enough, they don't break anymore. We published the first paper. Turned out to be this is the paper. Get me tenure here at Stanford. So this is the paper really, set the button of starting the whole research field of nanotechnology for batteries. So it's good to be not afraid of the old problem. I collaborate with my colleague, Professor Bill Nix, a mechanical expert. Matt was my earlier graduate student, now a faculty member in Georgia Tech. We said, let's go to see what happened in this material. Let's develop a tool. We can see this. This is a holder. We call it a holder. You can insert into transmission electron microscope. Then transmission electron microscope can have this ability, can see your structure down to atomic scale. So if you zoom in right here, this is a single nanowire. We can connect with a gold probe, a tiny tip. And this is lithium cobalt oxide, that's cathode, that's anode. This ionic liquid with a lithium salt in there. You're building a nanoscale batteries inside electron microscope. Then you can charge it up to see what happened. So we can also smartly put some particle right there. We can watch the particles as well. Let me share with you, using a tool like this, we can first time visualize how the volume expansion take place, how this material will be broken if they're too big. So this is a movie. This is 200 nanometer. This is roughly close to about 1,000 times smaller than your hair, close to 1,000 times. This is 200 nanometer diameter. Once you put lithium in, you see this silicon nanowire volume expansion take place. And this silicon wire surface is coated by copper. This copper are those darker color material. They are broken by silicon wire. This expansion is so powerful. You just cannot stop it. And then now let's look at another video. These have some silicon particle attached to the wire. This is also 200 nanometer. This one is smaller. This one will be big, is a much bigger one. This is 800 nanometer in diameter. You're going to see this particle just grow bigger and bigger. And you see this interface right here. This is a crystalline core. This is amorphous lithium silicon alloy. Eventually, this particle just accumulate huge stress. It will not be able to contain the stress anymore. It's going to be broken. Once it breaks, and you lose capacity, you lose really a lot of lithium, lose silicon. So we need to identify what's the critical breaking size. How small do you need to make these structures so they don't break anymore? So why small structures will not break? Because you keep breaking things into smaller and smaller, there's got to be a limit. If you are smaller than the smallest structure, that lithium can break, they don't break anymore. That's the reason. So over the years, using wires, and we learned so much. I'm not going to bother you the 12th generation of material design. We try to solve interfacial stability problem for today's purpose. I will not be able to go into the detail, but let me share with you, this is a tough job. This is over 15 years of research, 12th generation. I'm a little bit superstitious, right? I will stop at 12. 12 is a good number. If I want to do something, I stop at 12 or 9 or 8 or 6. I will not stop at the 13. So this is 12th generation. That's it. So all done. So back in 2008, when we published silicon nanowire paper, I was contacted by, this is Sun Hill Road. All the money are sitting right here, right across the street from SLAC, right? People come to my office to talk to me about starting our company. I wasn't ready, but once you talk to people, everybody keep telling you the same message. You kind of start to believe in it. So I started to believe in it since oh, maybe I should start our company. So which I did. So in 2008, I founded Empress. Over this is now 14 years. And Empress has been doing a great job. I think I was also lucky as well. I didn't know how hard that was. It was good to be very young, right? You are not afraid of failure. You just say, hey, let's do it. Just go in and do it. So Empress is producing very high energy density of batteries right now, shipping to a customer. It's very exciting. A couple of weeks ago, Empress actually went for IPO. But it's a very tough time to be an IPO market, right? So Empress went ahead and do it. So we went to New York to ring the bell. And this is the whole board and also the management team. I need to say congratulations to the Empress team. It's their hard work to make this happen. But what's the lessons I learned through this process from labs to market? So let me share with you, this is the lessons I learned. First of all, it's very, very hard. It costs a lot of money. Venture capitalists put in the money. But what I learned from 2007, when the technology was invented, published 2008 January, and to now, lab to market. So what's the bridge you are really crossing during this process? Why it took 14 years? So you have to understand in our lab, we are working on this milligram of materials. What's milligram, right? 10 to minus 3 grams of material, tiny amount. And to go to commercial scale, you need to go to ton scale. And then to occupy big market, you have million ton. So many orders of magnitude difference, 13 to 15 orders of magnitude difference right there. And we usually work on an area of centimeter square, tiny area, right? To go to commercial scale, you go to meter square, 1,000 meters square, and then 1 billion meters square. Hi, many orders of magnitude also. And also in the lab, we work on this cone cell, this button cell, tiny, right, centimeter square. And then commercial product, this is like, right, like this size, regular phone size batteries. And when you go to electrical transportation, they will be much bigger. So from lab prototype, commercial prototype, and manufacturing product right here, there's so many technical risks manufacturing risk would happen right there. So this together is orders of magnitude you need to cross. So this requires you to have long-term patience, long-term support, going from fundamental and applied research to engineering to scale production. So luckily in the Valley, we have Stanford, we have SLAC National Lab right here, very strong fundamental basis. Across the street, Sun Hill right here, there's a venture capital money right there. You know, in the whole Valley, there's a lot of talent. It's all co-located right here. And to make this happen. So not easy. So this is the first topic I want to share with you. Now let's look at the second one. Well, you know, let's loop it back to the fundamental research. Why this is important? You know, throughout my battery research, I want to find out what happened inside the battery cell. If for most of you, you say, well, you don't do battery research. You say, battery looks very simple, right? One electrode is a reduction reaction. The other is oxidation. You write down the equation, that's it. But it's actually very, very challenging to understand what happened inside. For example, and battery materials are very fragile. If you want to go to atomic scale resolution, in order to understand how batteries fail, would you be able to do it? Electron microscopy, transmission electron microscopy is a golden tool to see atoms. So I really want to see atoms. This is a metallic lithium forming this filamental structure. If you want to zoom in to obtain atomic scale resolution, you are destroying this sample very fast. They're not stable. So, and it's very, very hard. This is the reason is you focus the electron beam to look at your materials. There's so much energy dumping onto these materials. It's like having a magnifier, right? To burn the leaves or burn the ants, you know, kids like to do because you focus the sunlight energy right there. So we need a tool for doing that. And in 2017, Nobel Prize was given to these three gentlemen developing cryogenic electron microscopy. This is cryo-EM for biology. They can study the protein structure. And we noticed this technique. It's so powerful. At Stanford SLAC right here, we hire one of the best cryo-EM expert in the world, Professor Chu. He joined in right here to set up a national center for cryogenic electron microscopy. I was learning from his research. I say, well, perhaps I can borrow this tool to study the battery materials because you can freeze your sample with liquid nitrogen. By the way, liquid nitrogen is very, very cold. I think some of you might be doing this experiment before using liquid nitrogen to make ice cream, right? That tastes really good. That tastes really good, but it's very, very cold. You can stabilize your sample. And it's also, how do you use low dose imaging? Low dose means, hey, let's don't use so many electrons, just use a very small number of electrons. To look at your sample, you can already get the image, so you don't destroy your materials. And there's also imaging processing and so on. So back in 2016 to 2017, I have two of my graduate students, Yuzhang Li and Yanbing Li. And also, by the way, we oftentimes make fun of these two. I say, you guys' last name is Li, that's lithium. So to work on lithium batteries, so that's a good pair, right, to work on this problem. So two of them developed this technique. And how do you freeze your sample into liquid nitrogen? Very fast and without changing your sample, right? And then while maintaining very cold temperature, close to liquid nitrogen temperature, and transfer the sample at the tip right here, insert it into gigantic electron microscope without exposing air. So they did a good job on that. And using this technique, for the first time, back in 2017, we were able to see this is atomic atoms of lithium for this metallic lithium structure for the first time. Everybody wants to see that for the past 50 years, right? Because the problem I mentioned to you, electron just coming in, destroy this this sample, you will not be able to see it. Now, first time we can image that. Not only that, a tool like this allow us to answer a question for about 30, 40 years now. Remember, I keep telling you about the solid electrolyte interface, that really thin layer of coating on your graphite particle, right? Silicon surface also have that as well. You know, what's the atomic structure of that layer? Nobody knows. And there are two hypotheses. One say, well, on this anode surface, this thin layer of coating, only about maybe about 20 nanometer only, but really, really thin. It's a mosaic model. You know, it's this tiny particle, lithium oxide, lithium fluoride, and other things forming these patterns, mosaic patterns, proposed by some scientists, at least in this paper. And it is another model, structure model, saying it's a layer model. You have a layer of inorganics. On top of that, a layer of these organics right there, forming the bilayers. Well, you might ask the question, you say, who cares? You know, what's the structure? Oh, you do care. We actually found out these two different structures will be very different and affecting your battery charging, discharging efficiency, the battery life. So using this cryo-EM technique we developed, we were able to resolve, you see, this is lithium metal, this is interface, this interfacial layer right there. This beautiful inorganic particle embedded into this green, highlighted as a green, organics in there. This is more like mosaic type of model. This is under one of the type of organic electrolyte. You know, in the whole battery industry, each company have their secret electrolyte. They will add in some called additive. It's like cooking, right? You add a little bit of salt, you add a little bit of pepper. You might add a little bit of secret sauce, make your dish taste better. Nobody knows what you add in. That's what the battery industry has been doing. So if you add in a secret sauce containing fluorine right here, right? I mean, this interfacial layer change, this green layer on top has this beautiful inorganic lithium oxide coating. Turn out to be this solid electric interface, this structure, give you much better battery performance compared to the previous one. So we are establishing now this correlation of performance with the structure. So now let me come to the battery safety. This is often very exciting because you got to see some fire burning right there. So and every time talking about safety, this all come up, right? Whether it's from the laptop, the phone, the car. Now this is stationary storage. And this keeps happening. So what's the reason why lithium-ion batteries keep having fires? Well, the biggest reason is that organic electrolyte right there is organic, that can be burned. But how do you make it burn? So this is a battery, right? Cathode and anode, two electrolytes are separated. For whatever reason happened right here, you cause a shorting. There's something going on, make your cathode and anode touch each other, will leak electrons through that. This will heat up your batteries. This reason might be due to, hey, you have manufacturing defect, your separator has a flaw right there. This might be due to you do overcharging. That's why your charging control system needs to be really good. If you overcharge your batteries, you can form this so-called lithium dendrite for shorting. Then you can also have accident or cell crash. So once you have the shorting, this will release a lot of current, right? A lot of energy. Then there's many fundamental processes taking place. Without going into the detail, you know, this just start to heat up. Eventually, this will start to catch fire and explode. So how do we solve this problem? Number one is prevent shorting. Detect the shorting before it happens. Now, let me present to you some of the ideas very quickly. First idea is, there's something going on. It is supposed not to be here. So we invented smart separator. This is a cathode and anode. The regular battery separator right here, if you have shorting touching these two electrodes, you release energy. You know, the battery catch fire. But can we put something in the middle in this separator? If this grows halfway, we can detect it. So we invented a new technology that can detect half shot. Apologize for this figure. And we also invented another technology. We say, well, what if the shorting really happened? It starts to heat up, but we don't want it to be heat up too much. We develop a layer of coating onto this current collector. That's current collector. And if you zoom in inside, this is a polymer layer with this metallic nano spike. You see spiky thing right there. At room temperature, they're conducting. If your battery cell heats up, this polymer volume expand. They're going to expand, will pull this particle open. They don't touch each other anymore. And this whole thing become insulated. This become a protecting switch. We show that this could protect your batteries from catching fire. The most recent one is very exciting, is come back to the structure again. This metallic foil only used in the past, only doing the function of coating the graphite particle in there, doing charging, getting the electricity in, taking the electricity out. I mean, it's not really that smart, right? Only doing this, I would say, the dumb job, right? So why don't we utilize this current collector? We've invented a tri-layer current collector. We put a polymer right here, that's polyimide, an embedded TPP molecule. This is a fire extinguished molecules into this polyimide and coated with copper. These are still conducting. We invented new type of current collector. Once this battery about to catch fire, this polyimide will release PPP, extinguish the fire. Let me share with you this video. The left-hand side is the regular copper foil current collector made into the battery. The right-hand side is our triple layer current collector. Let's look at the video. Now, you build the batteries. Now you want to use the fire and try to burn it. You're going to see the left-hand side is going to catch fire and continue burning. Now let's look at the right-hand side. You try to burn it. It's actually, first of all, it's much harder to ignite the right-hand side because the release of TPP, even you can burn it and it's going to self-extinguish after several seconds. So the right-hand side is much safer. We are hoping to have such a technology to go into the real world very soon to enhance the battery safety. So the remaining minutes, let me now share with you a very exciting topic on grid-scale energy storage. This has been a problem we've been thinking about, try to invent a new technology for a long time. It's indeed very, very hard. The reason is to go to grid-scale is a gigantic storage unit right there. And then the grid require you to go to smooth out the grid, make the electric grid very stable from minutes to minute energy storage, from hour to hour, day to day, week to week, month to month, seasonal, eventually. For example, in the summertime, you generate a lot of solar electricity, but wintertime, you don't have that much. Then you need to store the summer electricity, wait until winter, and then release it. So every year, you only use that battery for 1 to 2 cycles. Then this battery cost got to be really low, right? So far, we are $130 per kilowatt hour. Eventually, we need to go below this number. We don't know how to do it. And we don't even know how to do day-to-day that well right now. We probably know how to do 4 hours. And also, you want very long life. You invest such a big, a battery farm. If you only use for 10 years, no, economy is not good. You really want it 30 years or longer. 1 day per cycle, it requires 11,000 cycles. If you want to do 3 cycles per day, it's going to be 30,000 cycles or longer. You need very long cycle life batteries right there. You want it to be maintenance-free in all climates. Solar is usually in a very hot weather, right? Wind is very cold. Lithium-ion battery will not do. Well, I believe most of you have been skiing in Lake Tahoe. Take your cell phone with you and see what happened. Automatically turn off, it's too cold. The cell phone will not work anymore. It's because of batteries right there. So extreme heat and cold, can you invent a battery can do that? Needs to be very safe. So, well, 5 years ago, we looked into this problem. he say, well, what's the longest lifetime batteries, cathode chemistry ever invented in human history? What's the longest life anode chemistry ever invented in chemistry? Let's marry these two together. If they have not seen each other yet, let's force the marriage and see whether that can happen. Well, it turned out to be nickel hydroxide become nickel oxide hydroxide is the longest lifetime cathode chemistry, one of them, one of the few ever invented. For the anode side, it's water become hydrogen, hydrogen become water. That's the longest lifetime. So I was talking to my students, postdoc, I say, hey, let's force these two to get married, to produce, you write the equation, it's beautiful, you know, balanced equation. That sounds like it should work. So it did work. So we produce this material, this is the tank, you know, this is the kind of the rolling, similar as the cylinder cell I told you before. If you zoom in, this is the cathode separator right here. This is your anode with this catalyst to catalyze hydrogen become water. Well, when we invented this, I was very excited, but turned out to be, no, I was not the first one. And 30, 40 years ago, in the aviation industry, NASA has been using this chemistry for Hubble telescope for 30 years now. I just didn't know about it. But NASA's version was too expensive. They used platinum as the catalyst right here. Our contribution is put down very low-cost catalyst, replace platinum. Now it can be for a civilian use. So we made this cell and we show this can last forever. This is 10,000 cycles. After that, you still have 95% capacity retention. This can go more than 30,000 cycles, more than 30 years. This is, again, a tiny cell we do in the lab, centimeter square type of level, right? And we will need to go bigger to go to the real world. And not only that, we notice nickel, the price is not the lowest one. We have manganese, lead, and iron. This much, much lower cost. Come back to the very early style I was telling you. Storing energy is about finding that a metal ion can balance the charge. And we care about the cost for the very big system. So you look at this, manganese low cost. We actually invented for the first time of manganese hydrogen gas batteries. Here is a manganese 2+ can become manganese dioxide back and forth. This is hydrogen become proton back and forth. This is overall reaction. Without going into the detail, but this is a chemistry really worth looking at for the long term. This is going to generate very low cost batteries chemistry. So with this invention, this family of using metal with hydrogen, 2.5 years ago, I spun out in a Innovano company. They're building this gigantic battery cell with 4-inch diameter, 1 foot tall, and really showing this amazing performance, 0 accidents, can store energy across multiple hours, 0 maintenance, can go down to very low temperature, very high temperature. And you know what? Innovano just shipped the first product out to customer about a month ago, and just announced a purchase order from a major green energy company of 250 megawatt-hour. So I'm so happy to see this is a shipping container going out. So this is coming up big. Now talking about big, the last topic is very important. Let's imagine how big is big, right? This whole market. How much do you need? Let me give you some number. This is portable applications. I roughly estimate we'll need about 100 terawatt-hour for this mobile application. For stationary, we'll roughly need 200 in order to go to carbon neutral transformation, going to net zero. Total is about 300 terawatt-hour. Well, what does this mean, 300 terawatt-hour? Let me give you a calibration. Lithium-ion batteries has been commercialized for more than 30 years now. So aggressive building in the past decade. Now, if you count the current production, also count the announcement, people say they're going to build the plant to produce lithium-ion batteries. They haven't built yet. Count those in, it's about 1 terawatt-hour per year. We need 300 terawatt-hour. How many years do we need to produce this? 300 years. We don't have 300 years to do it. So how much materials, how big are these battery pack? 300 terawatt hour, roughly in the pack level, is about 3 billion tons of batteries. Well, what's 3 billion tons? Let's also calibrate ourselves. Anybody can have a unit to calibrate what's 3 billion tons right there. We have about 7.5 billion people in the world. Adding all the people's weight together, let's take a guess. What's the weight? This is my colleague Alumajang that I would like to use to calibrate people. Say, billion tons, what does it mean? It's only about 0.5 billion tons of human being, the whole world adding together. This is much more heavier. So how much material do we need to produce? These are the challenges we need to face. Scale production in order to produce this 300 terawatt hour. And we need to scale up 10 to 30 terawatt hour production. So the whole world production needs to go 10 times, 30 times more. And we don't have enough materials for doing that. We need lithium, we need cobalt, we need nickel, copper, manganese, we need a lot of stuff. We also need graduate students, we need high school, we need undergrad all coming in, right? This huge industry coming up. And then we need recycling. And we cannot afford to just bury these batteries anymore. Got to be recycled, circular economy. I don't have a good answer for doing that, but we will need to do that for sure. So with this, presenting this biggest challenge, I notice this high school student right here. You have 60 years ahead of you, so you got time. Let's look at the summary. I was presenting to you the future of the batteries. How high energy can we go to? Possibly, I believe we can get to 500 watt per kilo. Maybe we'll get to 1,000 by the time I retire. And we need tools to understand what happened inside the batteries so we can make better batteries. We need national lab, we need university to work together. We need long-term investment from the government to do so. The battery safety, we need innovative approach to completely solve that problem for the lithium ion. Otherwise, we all need to go to aqueous chemistry. It's much safer. That is really the case for this nickel hydrogen, manganese hydrogen gas battery. Use KOH solution, it's aqueous solution, base solution, base chemistry. Scaling in circular economy. Remember the number I give to you, 300 terawatt hour. That's the number we got to think about for the next 30 years. With that, let me end my talk by thanking all my students and postdocs. I have very talented pool of students. I think 2, 3 of them are sitting right here right now. You have questions, they can answer the questions. They are the hero doing all the nice work and a funding agency from particular Department of Energy. SLAC National Lab is a DOE lab. DOE has been supporting national labs, supporting university research for a very long term. This will continue going. With that, I'll stop. I will be happy to answer any questions you have, particularly from the very young students right here. Thank you very much.
So Yi, thank you very much. It's a really visionary talk, and we do have time for questions. I apologize to those people who are viewing us remotely. The questions will be just from people in this room. So here's the deal. Raise your hand if you have a question. The thing in front of you is a microphone. Just tap the little button in front of you when I call on you to speak. The microphone will turn red and you're on. Please, 2 people don't use the microphone at the same time. It gets confusing. So who would like to ask a question?
There's one all the way at the back.
Please.
Okay, thank you very much. Pick me first to ask a question. Yeah, a couple of days ago, just read an article that mentioned about metal hydrogen is very hard to transport because they're unstable. And now you just mentioned, I think on one slide, and there's a company give the solution, is that right? To transport metal hydrogen?
Oh, if I understand your question right, it's really about transporting hydrogen. That's hard. So these metal hydrogen batteries, when they are made, there's no hydrogen in it. Yeah, it's all water. Then when you build the batteries, putting the pack right there in the stationary storage, the first time you use it, you charge it up, the hydrogen starts to show up. That's probably what you refer to as transport hydrogen is very hard, but we are not transporting the hydrogen. We are transferring the batteries without hydrogen in it because it is in the discharge state.
Okay, thank you.
Next, please. Yes.
Hi, Professor. Great talk. Thank you. It was really stimulating. For your dream of flying to Boston, which doesn't really sound like a great dream, to be honest. I mean, what's the energy density of something like kerosene compared to the battery energy densities? You talked about target 1,000 watt-hour-kilograms. How does that compare with hydrocarbons?
Hydrocarbon is much higher, that's for sure, much, much higher. But you consider hydrocarbon alone, that's much higher. But once you compare the whole system, you need to burn hydrocarbon. You need to deal with all the exhaust. Eventually, hydrocarbon is still much higher at the whole system level. That's why you are more looking into, 2,000 watt per kilo, 2,500 watt per kilo for the whole system level of hydrocarbon. For the battery one, if you can get to 1,000 watt per kilogram of energy density, and the continent airplane is possible. But the long distance cross the ocean one will still be too hard. Energy density is not sufficient. So now you ask the question, why do we care about the battery so far away? So this short distance one will happen first for the airplane. For the long distance one, this alternative solution, I don't mean battery will be the solution for the long distance one. At Stanford right here, I can see the renewable fuel will be the approach for the airplane. That has a much higher chance to get to it's carbon neutral, but still can do long distance. So we need multi-approach going right now. For me, I would just love to push the limit and see how far I can go for the batteries. Oh, by the way, I work on renewable fuel as well, so as a backup.
I see. Maybe you can fly to San Diego in an electric plane.
I think that's possible. Yeah.
Okay, please. Yes.
Hi, Professor. Sorry, I have a really limited knowledge of batteries, so if I say anything,
Don't worry.
sorry.
It's
But
Completely fine. Don't worry.
I remember you mentioning that batteries they have like a hard time resisting extreme weather, extreme temperatures like cold or hot. So what is, if there are some possible ways, what are some ways that they would be able to resist that?
Yeah, that's a good question. The lithium ions, if you go to too cold temperature, lithium ion battery has this organic electrolyte, right? Because at low temperature, it becomes viscous, eventually get frozen. Once it gets frozen, it doesn't work. And even if it doesn't get frozen, if it's too viscous, lithium ion cannot move fast enough. That also doesn't work. If you go to higher temperature, and these are organic solvent have certain vapor pressure, start to become vapor. Now, maybe before that is a side chemical reaction start to kick in between the organic electrolyte and your cathode. This is a very complex chemical pathway. What limit is also high temperature range. Of course, then you say, why don't we invent new type of solvent electrolyte to solve that problem? Actually, that's an exciting research direction. Many scientists are doing that. That's all legitimate. So far, we haven't got there yet, but it's some promising data showing the particular low temperature one. I see there's some good stuff. High temperature one also has some good stuff, but having both low and high temperature all together is much harder. That's an active direction. Maybe you are in high school right now. That could be something you should think about.
Another, someone else, please, in front. Yes, you.
Oh, thank you very much. Mr. Tree, I have a question. I think several countries now, they focus on the breakthrough of nuclear fusion reaction technologies. And I think that's probably the ultimate technology to produce endless clean new energy. And of course, and your lecture here today is mainly focused on the chemistry technology, new materials. And no matter what in the future, still need a new material to hold the reaction of that nuclear fusion reaction. I think that's probably also gonna be a bottleneck. So I wanna ask, what's your vision about these two technologies? I mean, chemistry and also physics, to let a human being get like almost free and clean and endless and forever clean energy. Thank you.
Amazing question. So today I only talk about batteries. I have another set of slides put on my director hat as a Preco Institute for Energy. I have a wish list, top 10 technology we need. Nuclear fusion is one of them. I don't work on fusion, but I recognize so important. If we can get fusion to work, amazing. So fusion, every time I talk to my colleague Steve Chu, we always say it's 30 years away. Maybe now it's 25 years away, but somewhere close to 30 years away. Highly supported. People should work on fusion. Let's do that. You know, we can create another sun, right? So artificial sun, that would be amazing. So this top 10 technologies, other things takes longer conversation I can share, but I do have that slide. Indeed, I just gave a talk in the afternoon in San Francisco, just mentioned that. So that's a simple version of answer to you. That doesn't mean batteries will solve everything. No, battery will not be able to do that. And we need many other technology coming in. I have my top 10 list. Yeah.
Okay, thank you, Professor Tree.
Yeah.
Okay, there was one more question here. Yes, please.
Good talk, and especially on safety. My question is that you have shown all the chemistry on the safety. Did you get a chance to look at the various toxicity components and coming out of that? And also my second question is that at the end of life of any of these technologies, how do you handle recycling? Because you cannot recycle 100%.
Yeah. So the file, indeed, when we pick that TPP molecules, and there's a number of choices you could have for the fire extinguisher. We are picking the one that's most environmental friendly. I agree with you. There's other very nasty fire extinguisher. TPP is considered relatively safe, but I wouldn't say I fully understand its environmental impact yet. So I don't, because there's phosphate right there. If it's the burning is complete, it's phosphate, seems to be good. If it causes some others compound, and this requires detailed study. I'm not a complete expert on that. And then you mentioned the recycling. And so far, the two types of recycling method, the dry method, you know, you kind of burning organics away, you know, burn as much as you can. The prior process as one, consume a lot of energy. Otherwise, the wet process require acid or base. Oftentimes it's acid. So those has a high environmental footprint. So I would say people need to have the whole circular thinking. Everything they put in, everything comes out. They got to develop to the degree not polluting the environment. So I personally don't work in that area, but I will encourage people to look at that carefully. And there's many startup companies now and in the nation to work on those problems. And I think sooner or later, the circular requirement will need people to deploy all the technology needed to get to the fully circular. I believe we do have the technology right there, and it's just a matter of deploy that and what's the cost.
So last question, I think, sir.
So you've talked mostly about the grid scale storage. So your examples are all sort of chemical storage mechanisms. How would you say that compares to other forms of storage, mechanical, gravity, other ways to store large amounts of energy that's not sort of chemical?
So the storage grid scale having a different time requirement, minutes to minute, hour to hour, the technology could be very different. Minute to minute will favor the technology having virtually infinite number of cycle life, but can do this very fast, back and forth. So that's why flywheel is used sometimes, right? And supercapacitors could be used. That hour to hours, flywheel will be challenging, and supercapacitor will be challenging. Then the battery will start to kick in. And then once you go to day, probably still in the battery domain, 3 days a week, I believe about within a week, it's probably battery will be winning. Then you say going beyond that, what's that? Then the chemical field might start to kick in, hydrogen, by month-to-month storage. And it is also pump hydro. Pump hydro is always good. It's just how do you get permit? And the total capacity, remember, we need 300 terawatt hour. I don't think we have that capacity. I mean, if you pump hydro so far is probably about the global so far is about 1 terawatt hour of storage. That's it. After so many years of 100 years of accumulation. What's the additional capacity you can do? You can do gigawatt hour, many gigawatt hour. Getting another terawatt hour might be hard. And you say, well, there's also gravity. I respect that, raising up and down, and it all comes down to the cost at the end. Maybe my personal opinion is biased because I work on batteries, so I would just say within a week, it's the batteries winning it. And it's whether this molten, metal, molten salt can come up to play a role. It's all about the cost. So I need to wait and see. Their cost can really get down to, I'm looking for the storage solution. Per kilowatt hour per cycle is 1 cent for the long term. So let's see what technology can get there, right? And so far, all those technologies are still too high cost.
Okay, well, thank you very, very much for this inspiring lecture.
Thank you.
So Professor Shui and his students will be around for a while out in the hall. So please, we'll meet you in the hall outside this room, and those of you who have more questions, we can sit around and discuss for a little while. So thank you all for coming. These lectures continue, probably the next one around Thanksgiving. Please see the announcement, and lots more interesting things happen here. So I hope you'll come back and hear about them.